Welcome to this lecture, and here as I want to tell you that we are getting into you might say that the real analysis, the real higher dimension analysis, because we are going to study today function of more than one variables. So, how do I do it? Let us, without getting into too many details, let us start by actually very formally defining it. It is sometimes very good to be more formal than start telling stories surrounding it, but sometimes the other way is better. So, you consider a set U subset of Rn and consider f to be a function which carries every element of U to some element in Rm. So, this is the most natural form of a function in higher dimension, and this is what is called a vector valued function. Okay. And if m equal to 1, that is f is from U to R, then we call scalar valued functions. I will give you two examples, physical examples, to tell you that what is what. For example, if I consider a 3-dimensional situation now, 3-dimensional space, so in 3-dimensional space take any point x, y, z, and then you try to see the temperature associated with it. Temperature T is actually a function, say T, of the position. So, if x, y, z is on the plane, say you take a kind of projection here, if this is the point x, y, 0, it is on the plane, the temperature is higher, and if it is going up, the temperature is lower, if suppose you are climbing the mountain. So, this is a scalar, this is a real number. So, this is a real number. So, this is an example, the temperature at any given point in space is an example of a scalar valued function. So, given x, y, z, you can measure a coordinate point, you can measure the temperature. What about a vector valued function? We have already had an idea of vector valued function when we had started force, when we had started velocity. Just to remind you, let me go ahead drawing this. That okay, let a particle move along a curve, then at any point x, y, z on the particle, the velocity vector is tangential to it. Of course, all these points are changing with time, and we know that the velocity vector v x, y, z is usually given as x dot t, derivative with respect to t, derivative of a function of one variable, y dot t and z dot t. So, here is an example of a function which takes a point in R3 and maps it to another point in R3. So, this is the velocity vector, and so if I have not written it down, let us written it down. This is the velocity vector, it is called the velocity vector, represented as a function from R3 to R3. So, here you have these two things very well set and very well done, right. So, things are very clear now. So, let us take a very simple example, like if you want to talk about a function of two variables. So, let us just first concern ourselves with the case when m equal to 1. So, let us concern with just function of scalar valued function of two variables and three variables. Let us see that. So, let us just take an example to see whether I can talk about something. So, let me see. So, let us take a function say f of x, y, z is x square y square plus xz plus y square zx. So, this for example is a function from R3. This is a vector in R3 and this is in R, is a function from R3 to R, and these kind of functions are sometimes, these are not sometimes, they are always called, I am just slip of tongue, these are called polynomial functions, polynomial in x, y, z. And forms a very important class of functions. Let us go over a bit and try to understand how do we represent such functions, how do we look at such functions, because if you have a function from R to R, you know how to draw the graph of a function. So, consider a function phi from real line to real line. So, basically how do you write a function? Y is phi of x. This is something known to you. So, what you draw? You draw the graph of that function. So, you draw the x axis and the y axis, and then so each element in R you are just plotting the value of y. So, it could be like this for example. So, basically what you have done? So, what you have done for the graph of phi, so for the graph of phi, which we indicate as GPH phi, this will be the standard indication for the graph. So, it collects all elements x, y in R2 such that y is a function of x, y, x. This is the meaning of the graph. This is how the graph is written in a more algebraic form. So, in that or analytical form if you want to say. So, now how do I come and talk about graphs in higher dimensions? So, for example, if I have a function f from Rn to R, then what is the meaning of graph of phi? So, how do I speak about graph of phi? Sorry, graph of f. So, the graph of f, so here I have R. So, graph of f is equal to collection of elements x and y, where x belongs to R n and y belongs to R, that is x y belongs to R of n plus 1, such that y is a function of x. like you can visualize the graph of, sometimes some people would write when you have function of n variables, they want to make it explicit by telling that okay, there are n variables of it. This x actually represents a vector in Rn, so it has n coordinates. Some people would try to like it like this, but I want to write it in a very compact way, that x means in Rn. Once I say x is in Rn, it is clear that it has n components which you can write as x1, x2, xn, or whatever way you want to write it. So that fact that x is in Rn means it is a vector has to be clear, and this way of writing is much more easier because this compact representation will also help you to understand more advanced mathematics. Now you have to understand that when you are looking at a function from R to R, it is very easy to visualize it, but while you are talking about function from Rn to R, it is not possible to visualize it unless say n equal to 2. So let us see, we will now look into the particular situation when n is equal to 2, right. For example, if I say that z as a function of x and y, that z, and let us define this function as, let us take an example, z as x square plus y square. So which means what, I will have, so x and y will lie on the plane while its value has to be plotted in a 3-dimensional setting. So let me see how they would look like. So what I am trying to draw the graph. Okay. So what I am trying to do, so this graph looks like this. It is called a paraboloid. Of course, you can generate nowadays by the standard mathematical packages. So it is, everything is in the surface, nothing is in the interior, is hollow. It is like a kind of, not a pizza but a calzone, that if you go to Pizza Hut and all these shops, you will find calzone. So it will be something like this, or pita bread, right, maybe a better idea is to talk about it as pita bread. So pita bread, so anything is hollow which you can put in some vegetables or whatever. So this is the shape of a kind of a, not a fully a pita bread but a little slightly roundish pita bread. So this is not an ellipse that you see, this is actually a circle, but I am looking at it from my own perspective on the plane, and that is why I have drawn it like this. I am not drawn it like this. So it is slightly more keeping in view of the perspective, right. So this is called a paraboloid. So when you put x equal to 0, 0, it is 0, 0, and then you put anything that it gives you a non-negative number because these are all squares. So this represents what is called a paraboloid. Now once you know something about paraboloid, you can talk about other shapes. So what about other forms of functions, can I visualize them? It's here, this is an easy example, I will show you something more. So for example, if I talk about an example like this, z again is fxy, and this is equal to x square minus y square. So here again, if I have the three coordinates then the shape of this curve looks like this. So, this looks like something like a saddle. So, let me just outline it properly. It takes time to draw, but it's so it looks like a saddle of a horse. It is also called a saddle. It is also called a saddle function, or it is called hyperbolic paraboloid sometimes, but we will just call it a saddle function. So, what happens is that if I fix my x and just look at y as a function of y, it gets as a function of y, it gets maximized, and if I fix the y as a function of x as a function of sorry, it should be as a function of x. So, I think it should be x should be in this direction. Function of y. So, it should be x should be here and y should be here. So, this is this. So, these are the interesting fact that if I fix the x, then it is as a function of y, it gets just as a function of y, it gets maximized at y. This actually this y axis is cutting through the this part, actually the y axis is coming out of this part, this from this point, it is cutting through it. And if I fix the y as a function of x, it gets minimized at 0 0. As a function of y, when as a function, once I fix the x, it gets maximized at 0 0. So, this is the idea of the saddle. So, it is also called, those who take Pringle nowadays, Pringle potato chips, it is also called the Pringle surface, because it looks like the Pringle, the surface of the potato chips of Pringle. It is also called a Pringle surface. Another interesting class of functions that I want to talk about is the following. That is the class of linear functions. Now, you might be wondering that I am only talking about functions from Rn to R, R to R3 to R, R2 to R, and just keeping everything very simple. But what about giving a general example of a function from Rn to R? A very simple example of a function f from Rn to R is a function called linear function. It does not matter what is the n. So, how does a linear function constructed? Consider a vector C element of Rn given. That is, C is equal to the column vector C1, C2, Cn. Then define f of x as, if you want to be more precise, f of x1, x2, xn. If you feel that you are still uncomfortable with just writing a compact x, xn is C1 into x1, C2 into x2, plus Cn into Xn. What does such a function represent? You have seen this sort of function with P1, P2, Pn when we were talking about the diet problem. These kind of functions are called linear functions. So, what are linear functions and what is their definition? So, function f from Rn to R. So, Rn is the domain and R is the range. So, when we were discussing in the general form U as the domain. So, Rn to R and not R is not the domain but the codomain. So, not the range but the codomain. Range is of course the image of Rn under the function. So, now what is a linear function? We have defined what is a linear vector function. When the matrix we have shown that matrix is a vector function which is linear, but here for a scalar function the linear function is given in the following way: is linear if number 1 f, or this is additive, f of xy is fx plus fy for any xy and for any scalar, means any real number, for any alpha in the real line, f of alpha x is alpha of fx. This is what you have. This is called homogeneity. This property is called additivity property, and the next property. So, let us write down if you are confused. So, the property 1. So, the property 1, that is f of x plus y is equal to f of x plus f of y. This is called additivity property, additivity. Okay. And then this is called positive homogeneity. So, if you scale the vector x, you scale also the function by the same amount, that is exactly the meaning. So, this is called homogeneity, not positive homogeneity, because alpha is in R, sorry for the word positive. This is called homogeneity. Now, let us see what does a real function do, what are the real function look like. So, if you put say one variable x1, then that is f of x is equal to, this x is in R, say C1 of x, then this represents a straight line passing through the origin. But if we have two variables, say f of x1 x2 is C1 x1 plus C2 x2. What does that represent graphically? If this is your y is C1 x or z or whatever is C1 or x3 is equal to C1 x1 plus C2 x2, then what does this represent? This would represent a plane passing through the origin. So, it would represent a plane in 3 dimension, but passing through the origin, because 0 0 would satisfy, because if I put x1 equal to x2 both of them 0, then I will get 0. When x1 and x2 is 0, then f value is also 0. So, if I put x1, x2 and x3, so this is x, this is y. So, then this represents a plane, but plane passing through the origin. Plane of course is infinitely expanded in all directions. It sometimes becomes difficult for now. For example, if I look at a function like this, say a function phi x, y and z, and I call this w, and I write it as x square plus y square plus z square. Can I see the graph? Can I visualize the graph? The answer is no. No, unless you have some kind of a special way of viewing, because the graph is in 4 dimensions, the 4th dimension. Graph is in the 4th dimension, is in 4 dimensions. How do I tackle, how do I even visualize such a object? Is there any way to visualize such an object? What do I do in such situations? That situation tells us, brings us into the fore of an idea called level surface, and level surface becomes very important in subjects like optimization and where we talk about maxima and minima. But let us see, so we can't see the graph in 4 dimensions, but can we see some kind of its image, some kind of its shadow, not image, rather a shadow in 3 dimensions, and I can have an idea what it is. So that gives rise to what is called a level surface. So if I am in for this function, so level surface, level phi, level surface of phi is a set of all level surface at a given level. So level surface at a given level, say alpha, where alpha is a real number, is the set of all x, y, z in R3 such that phi of x, y, z is equal to alpha. Now let us come to this specific example where my phi x, y, z, I have taken this example as x square plus y square plus z square. Okay. What is a level surface of this? Now, for any alpha in R, to draw a level surface, so as you change your alphas, this level surfaces change. You can start with 0 and then 1 and 2 or 3 or anything in between and keep on increasing it. If I had function of 2 variables, then we will call it level curve. We will just write down on the side if we have z equal to fxy, then we have level curve. So whatever is in 3 dimension, I can see it in 2 dimension. I can get a feel of that in 2 dimensions. Level, so we will have a level curve instead. This idea can be defined even for n dimensions. Please understand that this can be easily extended just to have Rn here. X is in Rn such that phi of x is alpha, but that we can't even visualize. So we are just keeping ourselves to the situation where we can visualize things. So level curve is nothing but the same thing. We just level f is a set of all x and y such that f of x y is equal to alpha. So if you draw the level surface of this, what does it mean? x axis, y axis and the z axis. So, what do I mean by this? So, if I put x square plus y square plus z square equal to alpha, this shows that I am talking about all the points which satisfy this must lie on a sphere which is of radius root alpha and has a center at the origin. So, basically then you are drawing a sphere. Root alpha. So, basically what happens if I keep on changing my alpha, I will make if I keep on increasing my alpha, I will get bigger and bigger and bigger spheres. So, similarly let us try to draw the level curve of a paraboloid. This is pretty important, level curve of a paraboloid. So, how do I look at level curve of a paraboloid? Now, we have already drawn the paraboloid. So, it was z equal to x square plus y square. So, now you look into the fact that, so we look into the family of, so level curve, so we will look into the scenario where we put x square plus y square equal to some c. So, basically we will be drawing it with radius root c and center 0. So, basically the level curves associated with the paraboloid forms concentric circles with center 0. These are the level curves of, so if you just draw the paraboloid again, this time in 3 dimensions, what I am doing is I am fixing, so I am drawing paraboloid. I am drawing it as a 3-dimensional quantity. And since I am drawing it as a 3-dimensional quantity, let us fix this particular value of z, say z naught, and then basically take a plane which is perpendicular to the xy plane and cut at that and pass it through that point. So, basically what will remain, the intersection would be a circle. And in that circle, what would be the scenario? Basically, they will satisfy at every point of that circle, the z value is z naught. So, any point you take here has a coordinate of the form x, y and z naught, and this so which means it will satisfy the equation x square plus y square is equal to z naught, because that is the form of the function, z's value is z naught. So, hence basically you then what you draw, you just keep on dropping perpendiculars on the xy plane. And so on, you see that circular, the level surface has been, the level curve has been formed on the xy plane. So, that's the story. I guess we have now got a fairly good idea as what are surfaces, how we can visualize, what are functions of n variables. You see, I will just revert back that why we called it linear programming in the last lecture, because we were actually minimizing a linear function. Programming term came that the history is different, but we were minimizing a linear function subject to linear constraints, and that is why we called it linear programming. The objective that we wanted to minimize a function was a linear function. So, some examples of functions, how to define functions of more than one variable. We have pretty good idea about how to draw their graphs and how to visualize them, at least for functions defined on 2 dimensions and 3 dimensions, and some functions about n dimensions which can be easily defined in n dimensions like the linear functions. There are many ways to do it. For example, the x square plus y square, z equal to x square plus y square is often called a quadratic function. So, there are many forms. I am not getting into details, so some exercise can be given. So, we stop here today's talk, and tomorrow we are going to speak about the notion of limit continuity of a function of 2 variables, and then talk about the notion of derivatives, the notion of partial derivatives. That is what will play a very important role in tomorrow's discussion. Okay? That is why the lecture is called partial derivatives and continuity. Thank you very much. Thank you for giving a good amount of time to listen to me, and I hope you are enjoying the course. If there is anything that you want to tell me, there is anything that you want to share with us in the course, please do write on the forum. We will be back, or my TAs would be answering you as soon as possible. Thank you very much.